Oui, je suis belge, mais je suis flamand, alors français, oui. It would just be embarrassing. Um, so, right, first of all, thank you very much, Jeff, for the invitation, and thanks very much, everybody, for coming here and the school for hosting. Yes, so what am I going to talk about? That's a very good question. I've done lots of very different things. I usually don't fit very well in a particular bucket. I'm a web developer or backend or machine learning thing. I like to do different things. And also, I care very much about the applications I work on. I really like that connection with the ultimate, with the end application. It's more interesting to me than actually technology in itself, though technology is interesting as well, of course. But also, so this talk will kind of talk about three things I'm involved in, which I find interesting. It's going to be an application level talk. I'm not going to go very deep down into technical bits. I'm going to give more of an overview, because there's at least three full separate talks in this, and I can't cover everything. But I just think these are things that I find interesting and I like talking about. So, and I have an audience. You can't really go anywhere. Well, you could, but so yeah. So that kind of sets the scene a bit. Right, so beyond ad clicks. Now, I called it this because this goes back a few years. I had a friend of mine who was working very much on ad click prediction. So you have a web page, it serves some ads, who's going to click where, and which ads should I serve, etc. And you know, he made a lot of money. He was a good job, but he always used to complain that he didn't really, wasn't really that socially rewarding to him to be looking at, which ad of women's underwear should you serve up to people. And me too, I'm not particularly interested in those kind of things. So, I always try to find those other more interesting applications. Not to say there's nothing technically interested in the other side. Anyway, so beyond ad click. So, yeah, first of all, I've given a bit of background, but there's actually three things that I kind of interest me. So at the bottom, I'm a computer science person at heart. That was my original education. I like code. I spend a lot of time in an editor. And then that's kind of my background. However, I've also always been interested in more the physical side of things. So I like tangible things. So I was always drawn to big machines and the engineering side of things, which is kind of illustrated by top left. So I did a lot of work in aerospace. I've always had an affinity for underwater robotics and drones and things. So I really like that kind of engineering aspect. I also, on the far right, have always been very interested in kind of the interface between technology on one hand and the humanitarian conservation side on the other hand. So I spend a lot of my time volunteering for various organizations. I did a lot of work for the World Bank. I've done various projects in this kind of space. Development, ICT for D, that kind of area. And ideally, my perfect job is I can kind of mix elements of all three. And then, disaster robotics, and there's certain things that fit in those categories. But that's kind of my space, what I really like. And I know Jeff from London. I co-organize the London Algorithms Meetup and the Machine Learning Meetup. And if anybody's ever in London, I would suggest you do come along. It's a great community. And we got some really interesting companies and speakers. Anyway, right. Oh, yeah, and this is kind of my own pet project, which I'm just struggling to find time for, but I will get to eventually, is I really, really, really want to build an autonomous litter robot. And I already have, some ideas, and I've got a chassis, and I've got, some stuff going, but still a lot of work to do, but that's kind of on the side, which I really like to spend time on. Anyway, and my day job is about 6 months ago, I joined Oxbotica. We are a mobile autonomy company. We work on self-driving vehicles. Though I have to stress that this talk is with my own personal hat on. I'm not here representing Oxbotica. I'll just mention kind of the work we do, but, that's a separate hat. So right, and so three themes. I'll start off with ground-penetrating radar and landmines. Who knows anything here about ground-penetrating radar, GPR? Anybody? No? Okay, fine. Who knows what landmines are? Who's done some work with landmines or humanitarian organizations or? No? Okay, cool. So I'm going to talk about this, but first of all, I have to stress, I have to give massive credits here, mostly to Patrick Carson from UCL, who we did University College London, we did a lot of this work with, and who really did a lot of the heavy lifting here, and also Max Jacobs at SkyCap. So first, okay, GPR, ground-penetrating radar. So a radar that penetrates into the ground. And in terms of what you need to visualize, this is the kind of hardware. So traditionally, you have some kind of cart, and you've got like big metal box that's typically antennas. You've got a sending and receiving antenna, and then you've got a control panel at the top which just does some signal processing. And typically it's a cart you kind of push forward like a pram, but in some cases you drag it behind you. And so the antenna, it's telling me I should take an RSI break. Sorry, I'm going to turn this off. So I don't get good posture and all the rest of it. So let's quit that. It's interesting. I thought it would go away. Okay. Yay. Right. So how does this work? So in this case, you drag something behind me. You have a transmitter antenna which sends a signal, an EM pulse, into the ground at a particular frequency that will travel through the ground, and it'll hit an object which will reflect back, and you can look at the pattern of the signal you get reflected back, and you can look at that pattern and do some interesting signal processing to figure out what's actually underneath in the ground. That's a kind of very high-level view. That's the kind of intuition behind it. And then the idea is you get different patterns will give you, insight about what objects are underneath. So as an example, this is traditionally used very much in the utilities industry. So if you're looking for pipes or cables or such are buried in the ground, because you're gonna build a new intersection or a new bridge or whatever, you need to dig up a road. You want to make sure you don't dig through the cables or break any pipes. So you use GPR to do a survey, and that will then tell you where the cables are, and then you can work around them. And typically the responses you get for these kind of things are these kind of parabolic shapes. And the reason it's a parabola is because actually you're moving over the ground, and if you look at the travel distances the pulse takes, you can work out it's actually supposed to be a parabola, but that's less important. But the idea is, different objects will have different parabolas and different shapes and different intensities, and that way you can work out what's underneath. So it's obvious that this is. I had a lot of disagreement with salespeople who kind of sell GPR. Oh, it's like a photograph from underneath your feet. This doesn't really look like a photograph at all. But as a sales pitch, it works well. But many people come away disillusioned. Right. So it's not magic. It's a very general tool, GPR. You can use it in lots of circumstances, but it's not magic. You just can't magically see into the ground. A lot depends on the type of soil you're dealing with. More particularly the RDP value of the soil. So every soil has a kind of conductivity, how well your signal can penetrate through it. And it ranges from somewhere between, I think it's 1 for air, so then, essentially no resistance for the signal to travel through the air, to, like 81 for water. So trying to get an EM signal through water is extremely difficult, so you're not going to get much penetration. So, and of course, the soil you deal with, lots of different soils, there are lots of different characteristics. So depending on what type of soil you're dealing with, if it's very wet, you're not going to get much penetration. If it's very dry, it's like a desert condition, then you will get high penetration. So there's a lot of variation there. And also you've got the conductivity of the soil. So some soils, they're very conductive, like clays, for example, and they attenuate the signal. Or you've got even magnetic soils in some cases. Or salinity, for example, saline soils are a big issue because they weaken the signal. And what does that mean? Is that your signal won't penetrate very deep, so you won't be able to see much other than maybe the first 10, 20 centimeters or whatever, depending on what system you're using. But anyway, so it's just physics. There's nothing magical about it. And so you're sending out a pulse with a particular frequency, and then depending what frequency you use, you can either penetrate deeper or less deep. So if you use a very high frequency, so you're talking about 900 megahertz, for example, you can only penetrate on the order, again, it all depends on many factors, but let's say roughly a meter. And this is with the antenna stuck on the ground, pretty much. So you can penetrate about a meter. So that's not very deep, but you're using a very high frequency, so a short wavelength. So that means you've got quite high resolution. You can pick out small things. On the other hand, if you go for a lower wavelength, let's say 100 megahertz, you can penetrate much deeper, 10, 20 meters, but much longer wavelength, you're not going to get much resolution. That's the trade-off. It's fairly intuitive. And so you get these scans, these radargrams. So this is a kind of vertical slice into the ground, and you see the parabolas. And then some interesting post-processing you can do is you can take horizontal slices, and you can stitch them together in a cube. And then you can look at the cube from the top down as a bird's eye view. And then you can also look at particular features. For example, if you're doing an archaeological survey this way, you could, by building that kind of representation, you can kind of see the foundations of an old building, for example, or a tomb or such. And once you have the 3D cube, you can then start doing isosurface extraction and try to extract objects that you might be interested in, maybe it's an old burial site or some pipes or whatever. Again, details are not really important, but it's just to get an intuition that you're pushing this thing over the ground, you get these parabolic shapes, and then you can layer all these scans next to each other into a cube, and then you can start extracting features from that cube and to see what's underneath. So, general purpose tool, but what we're particularly interested in is landmines. So can you detect landmines? So GPR has been used for landmines for quite a long time. GPR itself has been around for a long time. But actually processing the data is very, very tricky and requires a lot of human expertise. But the idea, that, again, the intuition is fairly obvious that you have different types of landmines and they give different types of returns. And can you, by looking at the returns, figure out, first of all, is there a landmine, yes or no? And maybe you can even figure out what type of landmine. Now, and just I should note, here I'm focusing on humanitarian demining, which is very different from demining in a military context. So I'm looking here at humanitarian demining. So mines which have been around for a long time or laid down in times of conflict and now need to be removed now the conflict has been resolved. And this is, as you can obviously see, a very delicate and very dangerous process. It typically involves a lot of time sitting on knees and very carefully with a stick probing to figure out where the mine is. It's extremely slow, it's extremely dangerous and time-consuming. And there's various sensors people have developed, but typically, a lot of it is just on your knees and poking. But so the idea was, okay, could we do something? Could we improve this process somehow? We're not going to solve the fundamental problem, but could we kind of speed things up a bit? And so that was the idea of using an airborne GPR. So traditionally, all GPR is cart on the ground. So the antenna is literally, is about, either dragged on the ground directly, or there's, it's literally like a centimeter between the antenna and the ground. But you can imagine walking a cart over a minefield is not a good idea, right? So the idea, can we do it from the air? But that raises all kinds of problems on many fronts. So the terrain is obviously problematic. If it's not a nice flat terrain, you're going to have a hard time with your cart. And obviously, if you step on something, it's going to explode, right? But the problem is, as soon as you take the antenna and you pull it off the ground, you have this massive problem where, yes, you're sending out a pulse, but 80% of the energy of the pulse is going to hit the surface of the ground and bounce right back. And so you get almost nothing penetration. Everything just reflects back, pretty much. So suddenly your signal to noise is just horrendous. And of course, you lose penetration depth. There's just no way around it. You have to penetrate that top layer, which is problematic. So and currently, there's not much that exists at the types of wavelengths you need to be able to accurately detect landmines. And then, a landmine, we're talking anything from an anti-personnel mine, which is the size of a fist, let's say, to a large anti-tank mine. And obviously, the big anti-tank mines are going to be easier. But still, right, so we partnered with a radar company who did a lot of work and built a bespoke system, which, to my knowledge, is currently still unique in the world, which packs the whole thing down to something the size of a shoebox and weighs about just under a kilo. And that way, okay, we have something small, light enough, and still, efficient enough to actually get some penetration for the use case we care about. And so the first prototype we had was essentially that. You strap it to a multicopter, and you can start doing surveys. Now, of course, the catch is you have to fly about 1 meter off the ground. If you fly 1.5 meters off the ground, you're not going to see anything. If you fly too low, you're not going to fly properly because you get ground effect or you bump into things. And so there's all kinds of issues there. And then there's all kinds of issues around how do you position accurately. Because if there's a landmine there, you want to make sure it's there and not 30 centimeters to the left. So you need to know very accurately where the drone is, and that also brings a whole bunch of questions. How do you do that? Again, whole separate talk. But anyway, okay, well, we have something we can start flying around.
Can you use NASA Skycranes to fly higher and not in front of them?
Sure. How much are they charging per hour? But yes, it would be awesome. Not sure about you sending these rockets onto a minefield. I'm not sure what that does, but maybe that's not a problem. All right, okay, so we can gather the data, but then we need to still figure out, is it a landmine or not? At which point currently you need a very, very well-trained person to kind of click through the data, manually try various filters and say, yeah, it's something here, something not. And it's extremely difficult. It's very non-intuitive if you look at it. So we can sit back and dream as a computer science. You say, okay, we have some data, and then we have some fantastic magic which happens and then tells us, oh, it's a landmine, it's a Coke can, or it's a rock, right? That would be like awesome. And we could build up this kind of picture. So we have some objects we were buried, and we can build up the 3D cube, and we can extract kind of the precise location in 3D space of where the mines are. That's kind of the aim. But it's utopia. Anybody who's done any work in this kind of area realizes it's utopia. It's something you could try to get to, but it has a lot of difficulties. And this brings me into another point. So this is just a slide I took from the Drones for Good competition a couple of years ago. And it says, could drones cure disease? And as somebody who's done quite a bit of work in humanitarian space, I mean, there's no, I have to think of polite words, but this kind of stuff really annoys me. If technology, people, as technologists, we always like to think technology is great, and it's going to solve all our problems, and it's going to, there's always a technological solution for stuff. But the real world is a lot more complicated than that, especially in the development context. I mean, something like this, it's ridiculous. I mean, drones are not going to, but you see a lot of this. And also, when you talk about landmines often to a technology audience, you talk about this, people go, oh, great, yeah, we have this wonderful machine learning system. It's going to detect these landmines, and we're going to save so many, hundreds of thousands of lives or whatever. It's a fantasy, okay? The problem's a lot more complicated than this. Technology is just a small part of the overall solution. So this is just, feet on the ground here. We're not going to win the Nobel Prize. But doesn't mean technology can't be useful. You just have to think about applying it in the right way and just be a bit more realistic. But there's a lot of this kind of stuff where people get carried away. But anyway, so, okay, we built some machine learning system. Now, this is kind of the ideal scenario, right? So this is some real data which was taken in Sweden. We're doing a survey, and there's a big pipe. And you can see this big parabola. The horizontal line is the ground plane. So that's actually, you still see that there's some bounce back, but also, because the transmitter and receiver are so close together, there's actually a signal that jumps straight from transmitter into receiver, and you get this very strong response. But okay, you do get penetration, you can see the big parabola. And you can imagine from a computer vision point of view, you look at that, can you pick out the parabola? Sure, I mean, looks easy, right? The problem is the reality looks more like this. So this was, I think, some submunition that we buried at a military test site. And this is kind of the real data. And then you can very, very faintly, you see a little bump. It's all kind of hazy. But that's what the real signature looks like in this case. So that's a lot more tricky. Here's another one. And here, actually, you don't even see the landmines themselves. But what you do see is disturbances in the top layer of the soil where we dug the hole to put the landmine in, and then we close the hole again. And the density of the soil where we dug the hole is different than the surrounding density. And so that's why you see this kind of washed out effect. And this is what, like 30 centimeters deep or 40 centimeters? Definitely not more than that. So it's tricky. And the reason is you've got all kinds of interference going on. So there's a signal going from transmitter to receiver. There's some of it which goes down to the target and bounces back, but some of it goes up and hits a tree and comes back down. You've got interference from cell towers and cell phones and Wi-Fi or whatever. It's really tricky. You get a noisy picture. And then all of this depends on the weather as well. A survey on a wonderful day like this might be great, but then it rains and you go back tomorrow. You ain't going to see anything because there's all water in the soil and your signal is not getting anywhere and your picture is going to look completely different. So it's a really tricky problem. And then there's the issue, you got lots of manual expertise and you need a lot of time to collect the data. So this is the idea, could we still, what can we do with machine learning? It's come a long way, there's a lot of very powerful methods, so what can we do here? But of course, ideally, we want to do this in a supervised way. Let's not make the problem too hard for ourselves initially. So what can we do in a supervised way? We can go out and spend a lot of time digging holes and burying mines, or we can try to simulate stuff, and which is what we tried to do initially. And luckily, there's a great tool out there called GPR Max, developed by the University of Edinburgh, which does actually a fairly reasonable job of simulating different soils and different responses. And so you specify your setup, you pick a type of mine, you pick a depth, you pick a soil type, and you simulate an antenna moving across the field, and you can get back, you do some physics, and you get back a response. And with that, we can start building up a pipeline. So we define some variation in mines in different soils. We generate some input files. We perform the simulation. We take the simulation output, transform it into an image, and then we can do typical machine learning stuff, right? Train, validation, apply your classifier, and rinse and repeat. So we've taken an image processing view. You don't necessarily have to do that. You can treat it, you look at the physics and see how the physics work and then try to work backwards from there. Both have their merits. But at this point, we thought going the vision way, since there was so much progress in computer vision, and also it's fundamentally it's the way the human approaches the problem as well. That's what we try to look at. And so now in the older version, this is how we'd simulate heterogeneous soil. We'd simulate different types, different patches of different soil. And then we'd run the simulation. We get a picture like this. And we'd stick in a mine, which you can just about see here, and you got a bit of a response there. OK, and that kind of seemed to work. Oh, and yes, for dev people, this was all implemented essentially in your standard Python toolchain. And as for machine learning, well, ConvNets are all the rage these days. They perform very well. So OK, let's pick a fairly standard ConvNet architecture. Rectified linear units. I think there's 4 layers, 4 convolutional layers, and some pooling. Nothing particularly fancy. We just picked something not too big, not too complicated, and just see where it gets us. And then we can think about how do we improve the model afterwards. And then we built up some data sets. So, starting with the very easy case, landmine, yes mine, no mine. And, you see the parabola and no parabola. And can we at least, let's not worry where the mine is, can we at least tell the difference between the two? And so you push it through your ConvNet, and actually you get like 99% accuracy or something ridiculous, really, really high. And then, you up the difficulty, you introduce some noise, etc. And actually still we were getting really, really high accuracies. You look at the filters, and yeah, you're picking up these kind of parabolic type shapes, and that kind of makes net seems to be learning something. Okay, and then you say, well, could we, again, very simple, can we see if we can localize the mine? And in this case, we just use a sliding window, but you could do something like overfeet and do it more efficiently. But again, essentially a sliding window approach, and you can kind of pick up where the line mine is. Okay, so this was actually quite encouraging. Even on the harder data sets with more noise, it seemed to be working ridiculously well, which was very suspicious. And then we thought, well, hang on, actually, and we started looking a bit closer, and there seemed to be some weird bug going on. And we thought, well, you got that strong line across the top, which is the reflection from receiver into transmitter. And actually, that's a very strong signal, which was masking a lot was going in there. And the way the normalization worked was actually throwing away a lot of the noise. And so that wasn't good. So OK, we fixed that. And suddenly, the picture started looking like that, which was a lot more challenging. But actually, even there, we were still getting accuracies around 70, 80%, which was higher than I anticipated. But in the meantime, GPR Max itself improved, and we were able to go from something like that to something like this, where here you could actually specify different soil properties in a kind of mixture model type way. And so we could get much more realistic conditions. And yeah, there was a paper on how to implement that, but that's less important. But essentially, we generated a new data set, which was much more realistic, made much more sense. And again, we push it through the ConvNet, but even then, we were still getting really, really good accuracies, like 90% easily, and with a fairly simple net without doing much effort. So again, that was encouraging, but still very suspicious. And these are just 2 examples of where we got it wrong and got it right. And again, we improved the localization side of things. And OK, seemed to work reasonably. You would make some mistakes, but it seemed to work well for the strong cases. And so in parallel, we started doing more manual testing as well. So we improved the drone, the radar was improved, and again, we started doing some more consistent field trials. So going out to the field, digging holes, burying stuff, flying over it, looking at the data, etc. And so in this one case, for example, we buried a whole bunch of random metal things from different shapes and sizes and different depths, and then so in this case, put them on a diagonal at different depths, and then you fly over them and collect the data. And then if you do the stitching process, where you stitch all the scans together in the cube and you look top down, you can, does this have a laser pointer? No? No, OK, well. And you look top down, and this is, you can kind of see there's on the diagonal, you see these red blobs, which illustrate the objects we buried. However, of course, if you know what the answer is, you can kind of say, oh yeah, you know, it looks really good. But actually, if you don't know what the answer is, it's still not quite obvious how many objects are really buried there and which ones are just noise. So you know, it's, you know, while this actually may look reasonably well if you know the answer, even still, it's actually still a pretty dirty picture. But that's already quite good data. So it illustrates really there's a lot going on. And also, eventually, what we want to do is instead of working in 2D, you'd work in 3D and try to, you know, capture the actual 3D geometry of the landmines, and hopefully that gives you more information. But anyway, so that's what we did. We collected some data, and this was kind of verifying is the thing, you know, is the kind of radar itself behaving as we'd expect it to do in a normal workflow. And that actually seemed to work reasonably well. And that's kind of the ultimate idea. Then you can geotag these things, and you can kind of create an overlay, and that's kind of from a high-level point of view, the type of user interface you want to offer people. And note that you don't necessarily have to be really accurate at predicting where a mine is, but it's also already very useful to be able to say, look, actually, I'm pretty sure there's nothing there. That in itself is an interesting, is a useful result. Yeah. So, okay, now we actually had some real data. We're doing all this work in simulation, and Patrick had been doing a fantastic job of building up data sets and tweaking the model, and, you know, and refining the way, making sure what we generate is as realistic as possible. And we'd compared with one or two papers put out by one of the US defense projects who'd been doing similar stuff, and their pictures also looked, you know, they were getting very good accuracies, and it all looked like it worked out. And so these are kind of 3 instances of some of the real data, and you can just about see the mines marked, but again, it's not obvious. But then we pushed this through the model, but the result was a total and utter fail. It did not work at all. It was, in pretty much in all the cases, it predicted with very high confidence, oh yeah, there's nothing there, it's fine. And so a bit of a post-mortem. Well, obviously the real data is quite dissimilar from the simulation data, though it was quite surprising. We'd expected it to be closer. There is an effect of the UAV and potentially some source of noise there. But also it was, you know, as you saw in the earlier slides, you don't always see a nice parabola. Sometimes you just see like a fading out because where the hole's been dug, or you've got other effects going on, which as a trained human operator, you kind of learn to pick up on. But as a machine learning model who's kind of essentially expected to see parabolas in various shapes and forms, then it falls over. But again, it's a starting point. So it was really nice to go through the whole end-to-end system from idea to building the hardware to collecting the data, doing everything in the simulation, refining the method, then applying some real data. And of course, it falls over, which is kind of what I expected. But the idea is then you iterate, right? And you start feeding in some real data with the simulation data, and how you do some good machine learning model that combines, you know, both sources of information. And so there's a lot of interesting stuff there. And so, you know, talking about future work, so this is where you come into, you know, more larger data sets, better models. And also, you know, there's a big issue, false positives versus false negatives. You know, in landmines, you can't treat them equally. If I say, you know, I'm 50% accurate, there's a mine there, or even 80% accurate, and, you know, what point is good enough, and you know. So, and there's thinking about the 3D aspect, but then there's other things you could do in terms of localization, et cetera, and active learning, and integrating expertise from a human. You can imagine a human giving feedback, et cetera. So there's lots of stuff you could do. But in any case, so far it's been interesting, and you know, we're curious to see where the project goes. So that's kind of a first little story. Any particular questions on this or comments? Yeah?
At what frequency do you have each new image in the radar?
From memory, I think it's like 140 scans per second. So think of it as 140 pulses per second that are going into the ground. So then it depends how fast you fly. If you really fly, they're all far apart. If you fly very slowly, they're all very, very close together. And so we're flying at kind of, I think it's limited to, I think it's 2 meters per second, so not particularly fast. And there's all other issues related to the drone and data transmission. How do you make the scale and battery life and all the rest of it, which I haven't touched there, but yeah.
Can you do real-time processing?
I'm sure well, you'd always want to collect a patch of data and look at, you need some context. I'm sure eventually if you had good enough algorithms and you'd be smart enough, you could, but yeah.
The reason I'm asking is because if you're somewhere hovering above something that looks kind of suspicious, you want to spend more time there and maybe look at it from different angles and stuff like that, which gives you more data points where it's interesting rather than looking for hours at stuff that obviously doesn't have anything.
That's the kind of thing you do. Currently, we're still in the process of does this actually work sensibly? And if we can get that to work in the basis case, how do we make it efficient? But again, there's all kinds of issues with the drone itself, endurance. You know, copter can only fly for 15, 20 minutes, which itself raises issues.
Yeah, sorry, just something you said about the field test. You said you dig the hole, put something in it, and put it back. And you say you can see the disturbance in the soil, so maybe it's also a problem in the approach. I mean, you can't really confirm by something.
No, indeed. And so, of course, we tested different conditions, and you try to compress the soil, etc. But other than going to a real minefield where things... but then there's still cases where... there are cases where these things have been laid down recently and you can look at soil disturbances. And people typically use thermal methods often for that because the soil cools faster or slower. But yeah, no, that's definitely a confound. Yeah.
Can you get more data by looking at angles, or is the Brewster angle too sharp and it doesn't work?
What do you mean by angles?
Can I look from here and look from here and look from here, and so I get multiple perspectives on the same bit of ground?
I'm not sure if it makes sense, because it's not... In a way, you're already getting different angles, because the way GPR works, you're sending out a cone into the ground. And as you...
Well, you would need two drones, actually, because if you want to look at an angle, you need to have a receiver that's, if you take...
Oh, yeah, of course, yeah.
You need two drones.
That's that issue as well. You'd lose a lot more information, I guess, on the reflectance. So I'm not sure it would help much, to be honest, but maybe.
Wait, so
yeah.
So my idea was that if I'm flying over like this and looking down, then I'm getting this solid space of lines like this, and if I'm looking back, then I'm getting a space with solids like this, and I'm not worried about bouncing things this way. I'm worried about bouncing things that way.
I'm not too sure it's that easy.
Probably not.
Yeah.
Okay, I'll drop it.
I'm not sure, because also it's not kind of, it's not a single line that's going. You're illuminating actually a sort of kind of, kind of like an ellipse on the ground, and all that information, that whole ellipse is being condensed essentially into one point, and that's the reading you get. And I think things get complicated, but I'm not sure.
Yeah. Two things. One is Dirk has more things to say, so we can ask more questions later. The other is, for the shy, you can ask your question in French if you are feeling more comfortable with that. Though the questions in English have been very well phrased so far.
Yeah. Right, yeah, indeed time. So anyway, that's kind of one project I worked on, which I thought was quite fun and interesting. And we'll see where it goes. There's still a big jump to actually getting this in the field day to day, but it was definitely an interesting project. Lots we learned. And often people ask me, oh, what about a metal detector? And actually, I could have included a video. This was, initially I thought there's no way you could put a metal detector on a drone and fly it, just because the sheer proximity you have to be on the ground and the interference with the motors. But actually, while maybe not particularly practical, we did prove the concept by having a drone and a coil, and the drone flies up and the coil lowers onto the ground, and you can fly around with this coil, and it takes good piloting skills, but with an automatic height control system. And if your terrain is fairly flat, it does work. It's not particularly practical, but that was something fun as well. Anyway, I guess in the UK, everybody would know what this picture is about. But since we're in France, probably nobody really... Does anybody just mean anything to people? No, of course, yeah. Huh? Yeah, Monty Python. So anyways, and now for something completely different. Yeah, anyway. Who's this? What do you... Wally, what do you call him in French? Charlie. Ah, okay, so everybody knows the game, right? Right, so where's Wally? Okay, we could sit here for a while, but anyway, Wally's somewhere there. So fun little something to keep you entertained. I had a similar problem, which was where's the orangutan? Anybody see it? Okay, well, actually, there isn't an orangutan in here, but it's good exercise. But anyway, so this is a project I did, well, I'm still actively involved in with International Animal Rescue. So they're a large animal rescue charity. They work in a number of different countries across a range of different species, anything from, from seagulls, maybe not seagulls, but from otters to whales and they do a lot of work with orangutans. And so they have a couple of centers in Indonesia, one on the Java and I think even 2 in Borneo. And so they're an animal rescue center, an orangutan rescue center. That's the one they have in Borneo. And so this is where, orangutans are an endangered species, but as babies, they look very cuddly and they're very smart and they're very intelligent. And people like keeping them as pets, which is not a good idea. And often they get abused as pets, or they get chained, to a cage for 10 years or whatever. And these animals typically go through very traumatic experiences. Or likewise, you've got a large palm oil business in Indonesia who are chopping down a lot of rainforest, which means orangutans are losing habitat. Often they end up in palm oil plantations, completely lost, etc. So a charity like IAR will take them in and try to rehabilitate them and patch them up and try to get them back into the shape they can be released back into the wild. And for some animals this works, but for some other animals they're either too old, too young, too traumatized, or whatever, and they can't release them back into the wild and they just stay in captivity. But of course the idea is to release back as many animals as they can. And so this then leads to the problem, okay, fine, you have an animal, you spent a lot of time and a lot of money trying to get this animal back into a healthy shape, and it's astonishing how much effort and resources go into this. And then you release it back in the wild, but of course you want to know that the animal survives for 2 weeks, 6 months, 6 years. How do you know it's still alive after 6 months? How do you know it doesn't die after 3 weeks? And so that's the post-release monitoring phase. So how do you monitor the health and the well-being of a released orangutan after it's, once it's been released? And this is actually quite intensive. They do this pretty much daily. They check up on the animal for the first few months, and then this tapers off over the years, covering roughly 2 to 3 years. They follow each animal to see how it's doing. And if it's declining very rapidly, they'll take it back in and iterate. But obviously, this is very human intensive to track their movement. And you don't really appreciate that until you're there in Borneo, up to here in the mud, mosquitoes around your head, trying to figure out where the damn animal is. It's quite intense. And also, once you can follow these animals day by day, which is what they do, almost 24/7, following an animal through the jungle. But then, you haven't seen it for a week. Where is it? Where do you start looking? It's challenging. So what tool do they have? And they only have this since a number of years, actually, is they have some small VHF transmitter implants. They're about this big. Should have brought some, actually. And they're implanted at the back of the neck where the animal has a fatty patch. And what these implants do is they send out a pulse, a keyed pulse, so just an on-off pulse. There's no modulation or no data encoding or anything. It's just simply on-off every 1.5 seconds. And every animal has a different frequency, right? So they get these implanted and the animals get released. And then you have the people on the ground can pick up the signal of the animal with the large Yagi antenna. Okay, great. You think that helps things. You don't have to keep an eyeball on it the whole time. But even still, the range of that antenna in the jungle is on the order of 200, 300, 200 meters, let's say. So that still only means like a 200-meter bubble, and all you get is like a beep. And then, so the way it works is hopefully you're within that 200-meter range, and then you hold the thing up, and then you point differently. You listen, where does the beep get stronger? Okay, it seems to be there, and you walk 20 meters that way, and then oh shit, I don't hear it anymore. It seems to come from there, and people wander around the bush trying to figure out where the animals are. And again, so this is an improvement. It's still extremely time intensive, and that's fine if you have 2, 3, 4 animals, but you have 50 animals. It just doesn't scale. And so how do you prove to your donors who are putting a lot of money into this thing is actually working? Right, so the environment is pretty dense. So if you tracking them on the ground, this is kind of the idea, what we have to go through. But the idea is, can we do it from the air, right? And can we fly above the canopy, easily cover a large area, listen for the signals, and then just come back and say, look, the animal is there. That's the idea. And again, we don't need a big, expensive manned aircraft to do it. We can do it from a drone, right? So that's essentially the problem I got on my desk at some point. So you sit down and spend lots of time thinking about this. And again, same kind of thing as with the landmines. So drones would be great. They can kind of take the needle in a haystack problem to a needle in a bale problem. You know, you can cover more area. However, it does not solve the fundamental problem. The fundamental problem is these rather crappy transmitter implants. Ideally, you'd want an implant that has GPS and talks straight to a satellite, and you could just monitor from your desk. The problem is, how do you get something that's small enough to be implanted and with a battery life that's anywhere near reasonable? But then you can say, well, why are we implanting? Why not a collar? And this is interesting. So especially the males, they have these cheek pads. And so a collar would interfere with their cheek pads and their behavior. So no, not going to happen. And also, they don't particularly have necks. So it would be fairly easy for them to slide it over. So then you think, OK, maybe like a wristband or something around the ankle. But again, they're so flexible, they just slide it right off. You could try to stick something on their back. But again, they're very clever. They're very strong. So that soon they'll start biting and pulling. And it's not impossible, but it's very non-obvious how you would attach some kind of transmitter to an orangutan externally with a decent battery life and a decent reception, and it's not too heavy, and the animal will gain weight, it'll lose weight, and how do you do it? It's very non-obvious. But anyway, so that's really the fundamental problem, and the drones are not going to solve that. And they're not going to save orangutans from extinction. I did a talk at some place, and the lady publicizing the talk with the headline, drones saving orangutans for, they're not. But again, given the use case we're dealing with, they're a useful tool that can solve a particular need. It's not the be-all, end-all, but it's a useful tool. Again, putting technology in context. And the core problem really is habitat destruction. That's what's really the core problem. And the more you read into it, the more you realize it's complex, it's social, it's political, it's even religious in certain cases. And it's just very depressing, to be honest. It's really not fun. Anyway, so we have a drone. So the idea would be, let's start very simple. Let's not make things too complicated. Can we just fly a lawnmower pattern over the jungle, and then come back, and you get some kind of heat map saying, look, there's an animal there, 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 and there. And that's great, right? And then you know where the animal is, and you can go find it and check it's okay, etc. So put together something, starting from a fairly standard off-the-shelf drone with a Pixhawk autopilot. Does anybody fly or build drones here? Nobody, come on. It's so fun. So a fairly standard multi-rotor system. A Pixhawk is a well-known autopilot. The hobby it's used, you can interface with it very easily. It's not particularly expensive. It's a great system to test with. And then to that, we attach up top an SDR, software-defined radio. Does that mean anything to anybody? Software-defined radio? Yes, so one person. But anyway, it's essentially, you're listening for a radio signal. You need to pick up a radio signal with an antenna. So we got the transmitters here, and we got an antenna, in this case, a loop. And so you're receiving this analog signal, which you want to turn into digital samples. And that's what the SDR does for you. It takes the analog signal and samples it and gives you a stream of digital numbers, a matrix, essentially. And that's what we want, because then we can start looking at that matrix of numbers and do some detection on it. And then we have a little embedded computer, and this is an Odroid, fairly powerful thing for the small form factor. There's 8 ARM cores in there, and we just run Python, and we have a little front end. And so in terms of technology, so you got DroneKit, lovely Python library for interfacing with the drone. You can do a lot of cool stuff. In this case, PyRTLS, which is a library for the SDR. And we got on the back end, we're doing processing, NumPy, Matplotlib, and the usual suspects. Now, anybody who's done anything with radio will probably realize, actually, this seems a lot of overkill. We're carrying around this big Linux box, essentially, to do a very simple pulse detection. And that's true. But actually, the more you dig into it, it turns out this is actually not a completely stupid idea. But also, it means I'm not a radio person. I could, it would take me 3 times as long to build a PCB and do something that's highly efficient and small, but I wouldn't solve the problem in any meaningful time. So this seemed like a good approach, and actually it turned out to work quite well. And then on top of that, we serve up a web application using React and Leaflet And again, the usual things you would expect. So the detection logic, how does that work? Again, I could go into a lot of depth here, but it's, again, not particularly difficult. You have a stream of samples, and then, some digital signal processing. You look at the time domain, and you can look at the frequency domain. Anybody here done DSP or? Okay, one person. Fourier transforms, does that mean anything to anybody? A few people, yeah, okay. The pictures will make it more clear. But the idea is, so as you fly through the air, and you collect 2 seconds worth of data. So you listen for 2 seconds, and then you do the processing, and then you decide, did I hear a pulse, or didn't I hear a pulse? And you just record that. And then the drone comes back, it lands, and then you run some simple post-processing, and then the user will interface with the drone over a Wi-Fi connection on the tablet and pull up the web UI, and you can see the map and the results and see where things are. Now, of course, it's not an exact science. There's a bunch of heuristics there. You're never going to be exactly correct. But you just need to have one good detection, and you're sorted. Right, and there's various difficulties that while an implant will say it pings at 150 megahertz, in reality, it's not exactly 150 megahertz. It kind of, because the transmitter is not exact, the clock's not exact, it'll drift a bit. And even the temperature can have some effect. And also the radio you're using, that's not exact. You'll tell it, listen at 150. It won't get it exactly right. There's some noise in there as well. And so it complicates things a bit. But the idea is this is the kind of information you get. So at the top, we have the spectrum. So we're listening, 0 is the center frequency. So let's say that's 150 megahertz. And I'm listening in a band which is about 750 hertz either side. So somewhere in there, somewhere in that spectrum, I expect to hear the signal. So that's the raw spectrum. So for every frequency, you have a power. And then you can add some, apply some filters on that, and you get out a smoothed. You can apply some filters and renormalize, etc. And you get out this curve. And then from here, you can start looking, do I see a pulse or anything? Now here, ignore this one for the minute. So here, there's not much going on, but this is kind of an example where you do hear something. So here you can see in the spectrum, there's a clear bump. And so this is where we've actually detected a pulse. And so this is where we caught something. And so you see there's a very clear peak. And again, it's not too difficult to pick out that peak. What makes it tricky is we don't know in advance where exactly this peak is going to be. It might be here, but it might be there. And this is quite an obvious one, but it's not always that obvious. There's a lot more noise depending how high you are, how fast you're flying, etc. So it complicates things. So that's in the frequency domain, but you can do something similar in the time domain. And I won't go into too much detail, but if you see how the Fourier transform works, you can do something similar. We know what frequency it's pulsing at, so we can artificially generate, we know what the pulse should look like, because we can mathematically generate exactly the pulse we know we're looking for. And then we have our raw data, and in the time domain, we can just do a cross-correlation of the pulse we know we're supposed to find with our raw signal we receive. And you do that cross-correlation, and you can look for high correlations, and again, that can then help you to tease out if there was something, yes or no. And often that is, and the two are a bit complementary, and often you won't see anything there, but actually you'll pick it up in the time domain. But again, there's issues because the frequency is not always exact, so it may drift. You don't know in advance where it is, so you have to do some other stuff. And so I ended up building, a Gaussian model of where I think the pulse is going to be with some uncertainties, and you can move things around. But anyway, I don't want to go into too much depth. That's kind of the intuition. So that's happening while the drone is in the air. Every 2 seconds, collect some data, do some analysis in the frequency domain, something in a time domain, and just essentially write the results down to a CSV file with the lat-long coordinates of where the drone is, which way it's pointing, etc. And what I'd really want to do is build out a proper Bayesian model of this, and because you've got different variables, you've got the location, but you've also got the signal strength, and you've got the frequency, and you could tie this into a really nice Bayesian model and do some inference, and it would be a great exercise, but I hope I get the time to go into that. But something simple, you could look at odds ratios and the samples, etc. But I won't go into detail. But so fine, this is all the coding, and then the very first test just to make sure this worked, we took an Inspire, which is an off-the-shelf drone, and we just strapped a big antenna to it with the one they use in the jungle, and we just hovered it above the transmitter and flew around a bit, just to see, does this work at all, or is the interference from the drone going to kill it? And turns out, well, actually, yeah, you can kind of do a heat map, and okay, it seemed to be roughly in the right places. Okay, proof of concept seemed to work. And then I spent last winter a lot of my time with my knees in the mud, in the freezing cold with the drone and hiding the transmitter somewhere, and they're just doing lots and lots of flights. Oh yeah, and this is short movie. So yeah, that was the base system I was using. There's a small stick antenna taped to the bottom. This was my ground control station. And I spent a lot of time like this. And you do an autonomous takeoff. I'll just skip forward. And we fly to a certain altitude. You can just about see the drone there in the corner. And I would just start simple. Start at 10 meters, and I do a lawnmower. And see what can I detect. And they say, OK, and I go to 20 meters, 30, 40, 50, etc. So I started at 10. I think went all the way up to, all the way to 120 meters, which is the legal limit in the UK. And actually turned out even at, well, okay, it's a bit dark, but even at that height, I was still getting signals. Now, of course, this is with the transmitter just lying there. There's no jungle in between me, which is, of course, a big difference. But again, start simple and test the principles. And then you come into land. So the whole thing is automated, which is nice. And then you run the post-processing. Oh, yeah, and the kind of pictures we get is this. So this was taken at 25 meters. And so this is essentially latitude, longitude. Ignore the different plots, but look at just the top row. And the star is where the transmitter actually was. And then the red triangles are where I detected something, where I think I detected something. And it turned out to work quite well that, obviously the star is in this big red region. So that means it was relatively accurate to where the thing actually was. But it took a lot of iterations, a lot of flights, a lot of playing with different antennas to try and iterate towards that. And that seemed to work out reasonably up to, even up to about, I don't know what this is, 120 meters. So in this case, I only had one detection, well, actually two, and it seemed to work out quite well. So then we took it to Borneo, and we went to first the site of the sanctuary itself, where they had a pre-release site where they take the animals and just it's a fairly small enclosed island where they let the animals go just to see how they behave in this kind of mock environment. And somebody else on the team had a DJI Inspire, so while I was doing the actual tests, we had a follow drone which was filming, which was really quite fun and quite cool. Yeah. Unfortunately, it's very dark, but so yeah. So I would again pick a height. I think it was around 50 meters. And a patch of forest, and you would fly up and down, up and down, up and down, and come back to land. First thing I learned that you operate in the tropics, and you operate in any kind of real-world scenario, things break. Things break a lot. And it's just... like with the GPR thing, as soon as you move out of simulation into the real world, it's a completely different ballgame. And there's actually these days, and I'm always very, very wary of anything that happens only in simulation. It's a completely different ballgame. Right, and so again, we can do the same kind of thing. We flew over the island, or a particular animal we're looking for. We got a very strong signal, which was really nice. And we could start getting plots like this. And it was only at this point, so in this case, we didn't know the true location of the animal. We just knew it was somewhere in the area. And actually, we couldn't have wished for better results than this on the first flight. So it was a very obvious hotspot. And so I would do the flight. I would show it to the Persian manager at the site. They would radio to the guy following the animal. They say, where is the animal? They would say, oh, it's here or there. And it corresponded really well. And so that was a real milestone, because at that point, the sanctuary actually started to believe, oh, hey, actually, this thing could actually work. And so that was a really nice feeling. But of course, this was on a mock environment. Oh, yeah, and then there's a web interface I built kind of sit on top of that. And you could look at the raw data, and you can, kind of Google Mappy type interface. You could see the markers, and you could, start the tracking and do various things. So then it was time to test it in earnest, so we went into the jungle, which took quite a while. And then we started flying from the release site, which is here. And so this was the only spot we found which was where we could take off. As you can see, it's quite tight. So this is an autonomous takeoff where we're going to about 100 meters. The animal is about 2 kilometers away. So we're flying up to 100 meters, then we dash out 2 kilometers, and then we do a search, and then we come back and land. Now, I had 3 telemetry systems, 3 systems I could use for knowing where the drone was at all times. All 3 failed, all for different reasons. So here we're flying completely blind. It was kind of let the drone go, and you see it fly off, and you kind of hope it comes back. And so here we pick the right angle, and then it kind of flies off. So then we'll fly away again for about 15 minutes. And then in this case, we were really happy. Around 15 minutes, I could see it. And then I had to take it down manually. And this was quite nerve-wracking because it's quite hard. You see the thing quite high up, and you kind of there's a bit of wind, and you kind of bring it back in, bring it back down. And this is actually the antenna, and this is a little receiver. So this is a square antenna stuck to the bottom of the drone. And so this was a really nice moment when the drone was back, like, wow, we did the whole thing. So then we all gathered behind the laptop and looked at the results, and no detections. Oh crap! But it turned out the animal had moved, and so okay, fine. And we had videoed the whole thing, as you can see, so we could because there was a hill in between, so we judged the altitude. Well, we can fly a bit lower, and we get better sensitivity. And so we did that, and we then sent the drone off again, and it took off, and it flew away. And then we waited, and then 15 minutes, I could see that on the transmitter it reconnected, so I knew it was within a kilometer. And then suddenly the signal went. We waited, and it didn't come back. And then a post-mortem showed that we'd lowered the height slightly. On the way back, roughly about a kilometer away, there's a big hill with some tall trees, and probably just hit the top of the tree and snagged into it. And so the drone is out there stuck in the tree somewhere, which was a shame, but we were quite, it was not unrealistic to expect it to happen. So that was interesting, and so that was round 1. The drone concept proven. Lessons: if it can break, it will break, and if you did not test that change, it probably will have broken something. It's amazing. And what you also see is robustness above everything. Much more so than efficiency. Anyway, so I'm now working on a version 2, aiming to test maybe in hopefully January, February of next year to take back. So it'll be a better drone. I've switched to a different computer and different detection logic, etc. And actually, this this kind of fairly open project. If there's people who are interested in this kind of stuff, I'm happy to talk. And there's also some interesting data from how these animals move around the forest and how they forage and which ones are successful in release or not, which from a data scientist point of view is also very interesting. And I gave a talk in London about this a while ago. And actually, since then, there were 2 people who came on board, and they got some data, and they're kind of exploring it. It was really good fun. And just maybe as a moral story, there's what somebody told me, which I always remember, who's working with one of these sanctuaries. And actually, if you look into this and you realize, about the habitat destruction, the way things work, etc., it is quite depressing. And the way this guy described it, he'd been doing this for 30 years. He essentially said, well, conservation is creating hope where there is none, which is quite depressing, but essentially that's in many ways the truth, which I think is interesting to remember. Anyway, I'm almost out of time. I have one more section, but I've kept that fairly short since, but again, it's something completely different. I don't know if there's any particular questions on this end before we switch over, or otherwise we can talk about it afterwards. Okay, yeah, right, so radar and drones here, still drones, but not landmines, but orangutans, different set of problems. We got some computer vision, machine learning, and signal processing. Again, lots of interesting things, lots of stuff I had to learn, and still need to get my head around, but it's always rewarding. You can build something that actually works. But anyway, so what I do in my day job is is again something very different. And again, so I stress I'm not wearing my Oxbotica hat, but this is kind of just to give an idea. So what we do is mobile autonomy. So you have a vehicle, and you want it to be able to navigate the world autonomously. The classical example that everybody thinks of is like Uber and their autonomous taxis, for example. But there's a lot more other domains. So our focus is on the software stack and building up all the algorithms and the control and the perception, et cetera, to do this, and that we license out to other companies to use. They might license the whole thing, or they might license small parts of it. So we're really a software company, but of course, we need to demonstrate stuff working on real vehicles. And so this is, for example, a car we custom built that we just use for testing and research and demo purposes. So if we have a new algorithm, or we change a detector or something, we deploy it in the car, we start doing some routes, and we test how it behaves. And so when I first arrived at Oxbotica, my first 2 months were essentially building that thing, literally from soldering wires and power and harnesses, all the way up to installing the software and tuning the algorithms. So, yeah, the classical handshot. And there's lots of fun testing, especially obstacle avoidance ones where, okay, you first test it with a cone, it seems to work, and then it's kind of, okay, we put a human there, and then you're standing there and you see the car coming, you think, okay, is it going to stop? It's going to stop? It's going to stop. Oh, shit, shit, it's not going to stop. And so this is a problem, you know, well, there were occasions where, you know, we were still tuning things, and the problem was you know, it saw you, and it was avoiding you. It's just not in a very human-like manner. But, you know, as a human, you're standing there, you think, oh, my God, it hasn't seen me. And just the moment you're going to jump aside, it avoids you. And then there's debate whether you want to avoid or should you just stop. And, you know, there's lots of choices to be made. Anyway, but, you know, there's lots of different applications. We now have this running quite a few different vehicles. There's been some work on rail, off-road, forklifts, and low-level autonomous transport. Actually, also some of the core vision algorithms are going on the ExoMars mission. So that's all, how do you localize based on just a camera? So all you have is a camera. How do you, you know, track where you are based on that? Again, you know, there's all this work builds off years and years of research at the University of Oxford, which I cannot even begin to dip into. But kind of the high-level theme, which I think makes the Oxford approach somewhat different, is it's all about experience-based navigation autonomy. So the idea being, so this is exactly the same scene traversed in different conditions. So we got in the snow, we got at night, and we got during the day. And things look very different. And so if you're localizing based just on a camera, this is extremely difficult because you can look for corners or features or things, but things look very different in different scenes. So how do you deal with that? Do you try to build one big model of the whole world in all possible conditions, or do you try to do something else? And again, there's not enough time to go in detail, but the philosophy is we want kind of local excellence over global mediocrity. So we want to be very good in specific places, areas, and we prefer that on trying to be average everywhere. So we maybe want to be very good at driving in Nantes, for example, and maybe a bit less so in Paris or whatever, instead of trying to build one system that kind of does on average everywhere. And the idea behind this is, again, we think of multiple experiences. So every time the vehicle goes through a scene, it builds up a memory of what that scene looks like. And so in this case, and you can have multiple memories and different and so there's a whole lot of logic, you know, when do you create a new memory, etc. But the idea is, so this is as we're running live. I think this is actually a guy on his bike with the camera on the front. So as he's cycling through, you're matching certain features and landmarks in your live image to what you have in memory. And you may have different memories of the same route. And actually, if you come to a complex intersection or things that will change a lot, or, you know, for example, trees that lose their leaves in winter, or things that change a lot with the environment, you'll notice you'll need more memories to kind of localize in that specific place because it can look a lot more different in different situations. So that's kind of the intuition. And the same concept works in different environments. So this is kind of, you know, urban city environment to a warehouse. So this is in Chile, the Atacama Desert, which is mimicking a Martian landscape. And that is, I think, just an off-roading environment. And then what you see is that, you know, areas which are fairly don't change much over time. You don't need many memories to kind of localize against them. But areas that do change a lot, you need more memories. And by having this dynamically change over where you go, you can get better performance. And that's really a core strength of the Oxford group. And that's really the localization side. So how do I decide where I am? And then there's all kinds of other work. And these are just simple examples. This is some recent work that was done in terms of if you're detecting obstacles, like in this case with a laser. So you've got a spinning laser. And those are your obstacles. And you notice the black areas behind it. So your laser can't see through people, so you don't actually know what's behind the person. But actually, as these people are moving and cars are moving, you can push this through a big recurrent net, and actually you can predict how people are going to move if you can't see them. So if I'm looking at you walking the street and there's a car that comes in front of me, I can't see what you're doing, right? So I have to wait till the car passes, and then the laser catches you again. But you can actually start using a net to kind of predict what the path of that person could be. So that's some interesting things. There's also, this is also something more recent, is doing road segmentation. So what is drivable? Where am I allowed to drive? Again, as a human, it's fairly intuitive, but again, for a machine, it's pretty non-trivial. And again, this is using a fully convolutional net to do image segmentation, where you're taking all the pixels and essentially assigning a label to each of the pixels. Is it road? Is it an obstacle? And what is drivable? So this is drivable, and the red is obstacles, essentially. And because you're doing this on a car, you got some extra information you can use. You know the car is on the ground, right? And you know obstacles are not going to be floating in the sky. And so there's bits of prior information you can use to generate data. And in particular, for this if you want to train a classifier on this, all you actually have to do is drive a route, and then you know the car has driven that route, so you know by definition that's drivable. So that can generate you labels, and then you can train a classifier on top of that. So if you want to generate training data, all you have to do is drive. So you can generate as much data as you want. And then you can push it through a classifier, and then you can get something out of it. And then interestingly, if you start applying this classifier where you drive, it starts picking up on these kind of things where it actually detects there's more than one option you can drive, which is interesting. And the full paper of this is online. Yeah, and this is just the very last slide I had, which is just kind of rolling video of various machine learning type stuff that we do, most of it fairly standard. Anything from pedestrian detection in 2D and 3D to cars to analyzing point clouds, etc. So I'll just leave this rolling in the background, but I think I'll end it there. So I'll just try to give, from an applications perspective, 3 different things I'm involved in, 3 quite different things, just to give you kind of flavor what else is out there at a fairly high level. But yeah, I'll end it there.
Do you have questions? Même en français.
Bonsoir, je vais parler en français. Pour la segmentation, là, j'ai vu les différentes couleurs. Est-ce que vous différenciez les objets mobiles des objets immobiles, de sorte à ne pas encombrer la mémoire des objets qui sont mobiles?
So am I right? Sorry, I can't answer in French, but so am I right? You mean, so in the road segmentation, with the 3 colors, the blue, green, and red, are we making a difference between stuff that moves versus stuff that's stable? Actually, yeah, if you run this, you'll notice, because it's based off laser data as well. So you have the, you know what's drivable, you have the camera, which captures the raw images, but you also have lasers, which tell you where the obstacles are, and you're training the net on that information. And yes, if you actually play it like a car that's moving, it will detect that as an obstacle and won't try to drive over it. So yeah, but then the network learns this implicitly. It's not something we tell it to. So the short answer is yes.
Et quand tu enregistres, quand tu fais ton expérience, tu fais ta mémoire, tu enlèves ces objets qui se déplacent?
Ah, okay, yeah. So the experiences, yeah, of course, you filter out moving stuff because otherwise, if you kind of so if you're building a map in a way, so if you're incorporating in your map stuff that moves, you're not going to have a very good map, because the next time you go there, that person or that cyclist won't be there anymore. So yes, part of that process is also figuring out, what moves, what doesn't move, and filtering that stuff out. Now, of course, if there's one guy who stands perfectly still and doesn't move, and you drive through, you might pick that in. But you have enough features to make yourself robust. But yeah, that's a concern. Yeah. Oh, and so this is similar kind of thing, but a completely different approach. This is using just a single camera and doing dense reconstruction to also figure out what's drivable and not. So it's not really a machine learning-based thing. Anyway.
For those of you who haven't followed it, the approach at Oxbotica is very different from Google's, for example, where Google is using their massive map database to figure out where they can drive. And there have been some amusing, they're very reliable, but there have been some amusing errors where their map is inaccurate, and so the car thinks that maybe you can drive somewhere where actually maybe it's just a map error. But that said, their safety record is astonishingly good.
Thanks. If we look back from the first DARPA challenge to today, as Jeff just said, we are now almost out there in the real world with cars that drive themselves. So a long way. Can you? I don't know much about it. Can you tell us a little bit about what's really important in there? Are the maps important? The cameras? Is it? What is it?
So that's a very good. Well. That's a good question, but also a very big question. And also, I'm not sure I'm really the best person to answer that in a sensible way. My gut feeling would be to say everything's important. One thing, so a video I sometimes show is, who saw the DARPA robotics challenge, or I forget what it's called, the one I think last year or 2 years ago, where you had the humanoid robots and they had to climb up ladders and they had to open doors, etc.
The one that Google won.
Yeah, essentially. Yeah. And there's a lovely video of the fail version of that, where you have sequence after sequence of a robot trying to open the door, and you see it go and it falls over, or another one is trying to get upstairs and it falls down, or all these. It's really funny. But actually, if you think, this is cream of the crop, right? And this is all really top-notch teams. And I find, in a way, that's the thing with robotics and also with AI, and this is just me subjectively, is that you really have to have all the various elements working together in harmony for the whole thing to come across and to work very well. If there's small, if there's a certain segment of your system, so you're anything from low-level control all the way up to high-level planning, if there's something, for example, in the control layer that doesn't work very well, that introduces an error that cascades, the whole thing can fall to parts, and it looks really bad, even though actually the error maybe have been quite small. And you could argue, okay, that's more of an issue with robustness and you designed better systems. But so I think that there's that element that every part of the system is really important to get it right, and understanding how does uncertainty propagate through that. So that's one thing. But otherwise, what's important? Well, it depends on the application you're doing, I guess.
If I really want to have a car out there that is self-driving, what is the most important thing? Is it the planning? Is it the detection? Is it the camera that kind of knows where it is? Is it the mapping behind it?
It's all trade-offs, I guess. Do you, if you get in a car and you say, okay, safety is the most important, right? I want to make very sure I do not run into people or not kill anybody. But okay, the end result might be a car that comes, and as soon as the leaf blows, it hits the brakes, and it goes a bit on, and then there's a shadow, and it hits the brakes because it might be something, and so you get a very poor, that's not acceptable, right? Or likewise, planning, you'd say, well, okay, maybe planning is less important, but if you go to the wrong place, so it doesn't realize there's some construction work and it drives into a ditch. I think it depends. There's certain trade-offs you have to make. You cannot be optimal in all cases. And so you have to think, what application am I working on? What's the trade-offs the best for that application? And what are the trade-offs best for the human? As a human driver, what do you want? So I don't know. I don't have a single answer as what is best. I think it depends what you're doing and how do you make that trade-off.
More questions? On any of the subjects?
So when you're looking at
road segmentation or finding whether something is a person, are you only getting a yes or no answer, or is it something like probabilities of something happening? Or, I mean, it's linked to what we were discussing right before. If you think something is a person, that's more important than if you think if it's a tree, for example, because you do not want to run over that person. But I guess my question is like, where do you draw the line on what's acceptable?
Again, that's not an easy answer. And also, you know, I'm not wearing my Exotica hat here, and there's only, you know, I obviously can't go into technical detail how we do everything and make all those fine decisions. So all I can really say is that, of course, it matters what's in front of you. Is it a cyclist? Is it a pedestrian? Is it a dog? Is it a football? Those things matter, and you want to behave accordingly. Doing that accurately is not easy. You've got vision, but you've got laser as well, and each have their own issues. So how, you know, there's some interesting work in how do you bring those multiple sensors together. But beyond that, I can't really say much. But yes, it matters. But things get complicated quickly. And then there's, you know, what comes down to what is good enough. And that may depend on the person, and how do you measure what that is, and what probability is acceptable. This then comes down to how do humans behave, and how good are human drivers, and should you just match them? Or there's a whole can of worms there, but yeah.
One more. What is the biggest challenge right now? I mean, when we look at these images from movies, I mean, there's a lot of processing going on, and I mean, each problem just detecting pedestrians or you know, categorizing objects between a ball and a dog, and you know, all these are problems by themselves that are not trivial. We know that. So all of this needs a lot of processing power. Is that a real issue today, or are we on top of that? And you know, can you comment a little bit where are we currently? I mean, if I give you 100 times more processing power, does that increase the security by what? By a factor 2, or?
Again, so I should, you know, again, caveat, I'm not necessarily the best person for that, and of course, I can only talk about roughly my experiences and what we can do and what I'm allowed to say about that. I can't speak for Google or for other companies out there who have, you know, may work differently. And just, computers are pretty fast these days. GPUs are very fast. If you're doing image processing.
So you need GPUs in there?
I'm not sure actually for that, the particular the road segmentation. I'm not sure if it was done with GPU or not. It might have been. I don't remember off the top of my head.
As of about 2 years ago, Google's cars had a suitcase-sized GPU supercomputer in the back.
Yeah, but it's amazing what you can do with current hardware. So I think we can already solve some pretty interesting challenges with what we have already.
Any more questions? So you'll have a chance to ask more questions informally afterwards. So let's thank Dirk once more.